All right. In this problem, we are asked to use the methods of the previous section to derive a formula similar to this equation, which works for when Q is much greater than N. And we want a formula for the multiplicity of an Einstein solid and the low temperature limit. So we want the equivalent formula when Q is much less than N. So from this section, we learned that Q was the amount of energy quanta in the Einstein solid, and N was the number of oscillators in the solid. All right, so the low temperature approximation means that Q is much less than N, so that the number of energy quanta per oscillator is small. All right, so to get started in this problem, the first thing we're going to do is write down our formula for the multiplicity. So the multiplicity for some amount of oscillators and energy quanta is approximately equal to Q plus N factorial over Q factorial N factorial. So that is just an approximation because the actual formula would have been Q plus N minus 1 over Q factorial, and this was N factorial, and then your N minus 1 factorial. But we can say that the number of oscillators is so great that that minus 1 hardly even is noticed. All right, so to solve this problem, we have factorials of very, very large numbers. These are on the order of the number of atoms in a mole, which is about 10 to the 23rd. So to take factorials of a number that large, we're going to need Stirling's approximation, Stirling's formula. Stirling's formula is that n factorial is approximately equal to n to the n e to the minus n square root of 2 pi times n. And since we have such large numbers, the stuff under the square root is just on the linear order, and so it can be ignored. And so we have n to the n e to the minus n for our n factorial. All right, so just as a useful formula that we'll be using, when you take the natural log of n factorial and you use this approximation, that's going to give you is the natural log of n to the n, and multiplication splits up a natural logarithm. So when this could have been written as n to the n over e to the n, that actually becomes division. So we get natural log of n to the n minus the natural log of e to the n. And so that's going to give us n times natural log of n minus n. All right, so when we go up to this formula up top and we want to take the natural log of the multiplicity, we do that on both sides. So the natural log of the multiplicity is, we're just gonna break down the natural logarithm like usual. The natural log of quantity q plus n factorial minus the natural log of q factorial minus the natural log of n factorial. So next, we can substitute our approximation. Pause this. Okay, so we're gonna use this approximation that the natural log of n factorial is equal to, or approximately, I guess, equal to this, and so that's gonna tell us that when we use that on this one, we have q plus n times the natural log of q plus n minus q plus n. And then we're still subtracting these two, so when we subtract this one, we're going to use it again. So we get minus, and then I'll say quantity q, right? Because we had an n here, now it's just a q, so we're just replacing everything with a q. And then minus, and then we just use the same exact formula here. So quantity n, natural log n, minus n. So now we want to take another aside to work with this logarithm, the term that says natural log of quantity q plus n. So what we can do with that one is we can say the natural log of q plus n, we're going to factor out the n on this. So that's going to give us the natural log of quantity n times, and we'll have, I'm gonna rewrite, well, q over n plus 1, which by the Taylor series approximation, for the natural log of x plus 1 when x is small, that means that the natural log of x plus 1 is approximately just equal to x. So what we can do here is take this and break it up. The natural log of q plus n is equal to the natural log of n plus the natural log of q over n plus 1. And what we see is the q over n here is just like the x there, where it's a small quantity. And so we can say that this is really just equal, or is approximately natural log of n plus q over n. That look like a q. So what we're going to do now is we're going to substitute this back in to our multiplicity, or our natural log of multiplicity equation. So we have the natural log of the multiplicity is equal to q plus n times this term, which is equal to this guy, natural log of n plus q over n. And then we subtract minus q, distribute the negative, minus n, and then we're going to distribute these negatives as well. Minus q, natural log of q, plus q, minus n, natural log of n, plus n. So we see that we get some cancellation here. The minus q with the plus q, the minus n with the plus n. And then multiplying these two binomials, we'll have q natural log of n plus q squared over n plus n natural log of n plus q minus q natural log of q minus n natural log of n. So we're getting close. We see that we have this cancellation here, and then we can combine these two q natural log, these two logarithms, and that'll give us a q natural log of n over q, and then we'll have plus this q plus q squared over n. And then we can note that when q is much less than n, this term here is negligible. So all that we'll have left is q natural log of n over q plus q. And that's equal to the natural log of the multiplicity. All right, so I'm going to write that on the next page. The natural log of the multiplicity said that was equal to q natural log of n over q plus q. So what we want to do is exponentiate both sides. That means e to the power of both sides. So that'll give us the multiplicity on the left side. And then we'll have e to the q natural log of n over q plus q, which we can rewrite as e to the q natural log of n over q times e to the q. And then we can pull the q up to the power, and we'll have e to the natural log of n over q times e to the q, and all of that, times e, and then all of that is raised to the q. So what that gives us, when these logarithm and anti-logarithm cancel, is we'll have a e n over q to the power of q, and that's our multiplicity. All right, guys, so that's it. That's how you would express the multiplicity for an Einstein solid when the number of energy quanta is much less than the number of oscillators in the solid.